Great. Thank you so much. All right, everyone, we are ready to go. So we're really excited about this next presentation, which will be covering complex structural claims. And we'll be doing that by way of case studies. If you don't mind hitting the next slide. So we have a few presenters today covering this topic. First, we have Yasser Kureni, who is the structural forensics practice lead. He has 30 years of industry and academic experience, over 1,000 forensic investigations conducted, and court-recognized litigation expert. We also have Amir Jamshidi joining us. He's a professional engineer in Alberta, British Columbia, Saskatchewan, and Manitoba. He's a forensic structural engineer with over 15 years of professional practice and experience. He conducts forensic investigations on residential, industrial, and commercial buildings. We also have Adam Lohanyai joining us today. He's a forensic structural engineer with 15 years of professional experience, over 500 forensic investigations conducted, including condition assessments, structural failure investigations, code reviews on industrial, commercial, and farm buildings. And lastly, we have Nabi Gudarzi, who's joining us as well. He is a professional engineer in Ontario, also licensed out in Atlantic Canada. He has 10 years of professional experience, investigates and provides repair schemes for damaged and under-designed structures. He conducts structural investigations on industrial and commercial buildings. So welcome to all of you guys, and Yasser, let's get the party started.
Thanks, George. Would like to welcome each and everyone for joining us today, and I hope that you did enjoy the first session of our discussion today. I'm sure I did. I learned a lot from it, and we are going to continue on this theme of failures and failure analysis instead of the microscopical investigations that our materials colleague engage in. We're going to take you on to larger components and structures. And the reason behind this mix of presenters that we figured the after lunch session is always kind of difficult to maintain the same level of interest after we all had lunch. So having 4 different experts with their own unique case studies, hopefully would entertain the audience and present a good mix of information. So we'll get right down to it. And what makes a structure claim complex? What contributes to the complexity of a structure claim? Typically, there is some sort of collapse took place, either partial collapse of the structure or even sometimes a full collapse of the structure. If the cause is obvious and known, that won't necessarily be a complex one, but unfortunately, when collapse takes place, like the cases my Dino and my colleagues in materials shared, it is not that simple really to immediately identify the root cause of the collapse. This type of identification for the root cause would require expert analysis beyond the simple visual inspection of the structure. And it's not surprising that multiple parties would have interest, and the different parties would try to deflect blame, designer blaming contractor, contractor blaming property owner for making changes after the fact. And what we found from our experience that oftentimes it is not a single factor that caused a structure to collapse or caused extensive damage to a structure. It is typically a combination of factors that lined up perfectly, causing the collapse. And it's not unusual to see that those factors revealed a latent defect that was at the heart of the collapse. So I will have the pleasure of sharing with you the first case study and it is simply a mixed-use historic masonry building where the file or the claim started as simply a fire loss, like any other fire loss, and unfortunately ended up with a total loss of the building, complete reconstruction. At the right-hand side of the screen, you see a photograph of the building that we were going to cover. It is a historic masonry building, over 100 years old, two-story, mixed use. You have some stores at the main level, then residential units on the second level. The masonry walls are double leaf load bearing, providing the support for the building. The floor and the roof were constructed of wood. And the story goes that one of the occupants on the second floor had some argument with one of his associates. The argument escalates, the person comes back and sets the building on fire. So the building is badly damaged, and a restoration contractor being retained as usual, the contractor proceeds with gutting out the building for the purpose of restoration. While doing so, the contractor finds that one of the exterior walls, the one that you're looking at this photograph, which consisted of two leaves, one exterior and one interior. The interior leaf of this wall was cracked, bulged out, and appeared to have sustained some water damage. Contractor brings this up to the attention of the engineer retained to assist with the restoration of the building. Decision being made to address this damage as part of the overall scope of repair for the building. And that would have been lovely and dandy, except that around the same time, there was some road construction going on the street where this exterior wall is located. Part of the road construction is to replace the sidewalks. You're looking at here at concrete sidewalks along the length of the wall, and part of the project was to replace those. So as a contractor, the road contractor now proceeded with the removal of these sidewalks. He causes the exterior leaf on this wall to partially collapse, and the building is condemned and reconstructed. So what happened and how this masonry wall collapsed? On the left-hand side here of the screen, you're looking at the exterior wall, and you see the part of the remaining portion of the concrete side walls that have been pulled out in this area. And by doing so, this stretch about 3-4 feet high by 40 feet long of the exterior layer, exterior leaf of the wall collapsed. You could even see a gaping hole here, indicating that even part of the interior leaf of the wall has collapsed. The very next day after the initial collapse of the wall, this entire section of the wall collapsed, both exterior and interior leaf. As I mentioned, the wall is a load-bearing wall, so by having the wall collapse, that impacted, of course, the floor, support for the floor, support for the roof, and impacting the adjacent walls. Obviously, the building was unsafe at this point, and there was an imminent danger of complete collapse. So the decision was made to have controlled demolition instead of waiting on the building to collapse on its own. So we're going to take a closer look at this failure mechanism for the wall, not at the microscope level as my materials colleagues did, but what you're looking at here on the left-hand side, this is the masonry wall. Masonry wall is supported on rubble foundation wall constructed of field stone. This box here represents the floor level, and on the left-hand side here you have the sidewalk. The masonry wall is two leaves. Those two leaves are connected by header courses. header units that goes across, tie the two leaves together. And in the construction prior to the incident, it appears that the exterior leaf, at least part of the exterior leaf, was bearing directly on the concrete sidewalk. When the contractor removed this one, that caused this portion of the wall to collapse as well. What's the impact of that on the load-bearing capacity of the wall? Well, when you have the wall in the original construction intact, two leaves tied together, you have, we'll call this full capacity of the wall, 100% capacity of the wall. Over time, and remember that's a 100 years old building, those connections, those ties between the two leaves starts to crack and separate. So now instead of having one intact thick masonry wall, you have a wall that's consisted of two layers acting separately. The impact of that is a reduction by about 50% in capacity. Half, reduce it to half. What would that be enough to cause the building to collapse? No, because in our structure design, we incorporate factors of safety such that any reasonable increase in the load would not cause a building to collapse. This factor would hover around or close to 2. So by reducing the capacity of the wall by 50%, we pretty much exhausted all the built-in factors of safety in this design. Now, if we move to the right-hand side here, we have the wall already separated into two separate leaves. And remember, this inner leaf has been found to be cracked and bulged in after the removal of finishes because of the fire. So it's already deteriorated. Now we built a section out of the exterior leaf of this wall, and our structural analysis showed that the remaining capacity of this wall now is down only to 15% of its full capacity when it was originally intact. There is no surprise that the wall fell, and the failure of the wall triggered the building being unsafe and caused the building to be condemned and needing to be reconstruction. So what caused the building to collapse? Well, the building was through 100 years old with its deterioration to one of the leaves of the masonry walls, up to 3mm wide cracks. The two leaves had already separated, and we have discussed the impact of that on resistance. But we found that there was some discussion as to whether fire contributed to the collapse of the wall. And we demonstrated through our analysis that even if the fire incident did not take place, the exterior masonry walls would have collapsed due to the removal of the concrete sidewalk. Once you remove this major load-bearing exterior wall, that compromised the structural integrity of the entire building and needed the building to be demolished and reconstructed. That was a case where it started as an unremarkable fire loss and unfortunately turned it into a total loss. Now I'm going to pass it on to Amir to share with you another case study.
Thank you very much, Yasser. Can you hear me, George, Yasser? I just want to make sure that.
Yes.
Okay, perfect. Let me share my screen here. Yes. All right. Can you see my screen?
Yep.
Perfect. Okay, thank you very much. Good day, everyone. I hope you enjoy the presentations. And as Yasser mentioned, we have a few case studies, and I'm presenting the second case here. This is regarding the uplift to a farm building. Okay, perfect, it's working. So a 1970s farm building located near Moose Jaw in Saskatchewan was reported that it sustained wind damage. So this event was the third time in a 5-year period that wind damage was reported for the same farm building. So the case was complex for the insurance company because they had 3 inspectors, engineers before us, and they could not find out exactly what's happening and what was the cause of the uplift and damage to the farm building. Um, so to give you a little bit background information on the farm building, the property was a single-story building covered with a gable roof and exterior finishes you can see on the left-hand side. Finishes consisted of sheet metal cladding on the walls and on the roof. So the farm was a 96 feet long by 48 feet wide, typical size, and enclosed by 16 feet high walls. So the gable roof on the right side, you can see that was framed with 25 metal plate connected wood truss, spaced 4 feet apart, pretty typical. And they were tied with the purlins spaced 2 feet apart. So the wall frame with pressure, the walls were framed with pressure threaded wood posts tied on the exterior walls. You can see the post here. This one, these are all the pressure threaded timber wood post. So, and there was a plywood at the bottom here, so you can see on the screen, which I will come back to this one on the next slides. So plywood panels were installed inside the building at the bottom of the exterior wall. So the posts here were all embedded in the ground and serve as the building's foundation. Also, two pressure threaded timbers were secured to the post at the ground level and all around the building to serve as a standoff below the metal cladding. You don't see that here. It was all around here, so you might be able to see a little bit of that here. So the farm building was equipped with a 24 feet wide sliding door on the north wall. The door bottom track were secured here. You can see that on the left side to both a concrete grade beam and the wall. At the time of our examination, the sliding door was not functioning properly. So roughly 2-inch gap. You can see that on the right side is a close-up view of the gap here. So roughly 2-inch wide gap was observed at the top between the door panels, and a wider clearance was observed near the corner between the sliding door here when it was open and the bottom track. So also a slight uplift and bowing in the roof and wall were observed. So you can see the uplift here. So probably if you notice here, you can see the shadow on the left photo here. So that clearly tells you that it was an uplift here on this corner. And also it was a bowing on the opposite side of the uplift on in the farm building. So also, in addition, a slight uplift in the post and the surrounding soil was observed along one of the walls. So this wall here, when we look at from inside, those plywood that I showed you in the previous one, it was sloped almost about 1 degree upward. So that was an indication that this end has been uplifted. So there was something going on there. So the uplift of the frontal side of the building seemed to have been an, as I said, ongoing issue for almost 4 or 5 years, and it was estimated to be about 4 or 5 inch. So if you're looking from the elevation view of the building, this is as the building drawing that we developed. So the uplift was around here. So the plywood sheet here, you can see that we put it here, 1/2 inch thick plywood. Um, Inside the building were installed later on after the first incident of the uplift. So they thought that that can help and alleviate the issue of uplifting around the corner. So it didn't help. What they did after, they used hydrovac. So hydrovac was used, was also performed on all timber posts. This is just the details of what they did. To remove the problematic soil and replace it with 1-inch tamper gravel around the wood post. So just for your information, hydrovac or vacuum excavation is a non-destructive digging process and is a method of suction excavation, which consists of injecting pressurized water and a vacuum system to dig out the soil. So they also did this one. So they added plywood inside, they did a hydrovac, and still the issue exists. So what I got into this project, just wanted to understand, okay, let's look at all from different angles and understand what it is. So we look at the wind gust. So either, because this building was almost 50 years, so either the 1965 or 1970 edition of the Canadian Code for Farm Buildings would have been in effect at the time the subject farm building was constructed. So both editions refer to the National Building Code of Canada for wind design values. So wind design data for the province of Saskatchewan was the same in both 1965 and 1970 editions of the NBCC. So if the subject farm building was engineered, it would have been designed to withstand a wind gust of 141 kilometer per hour. So this is based on 1965, 1970 NBCC design data for the closest city to the subject property. So based on the climate change and environment Canada data, the maximum wind gust recorded at the nearest location to the subject building was 89 kilometer per hour, which is less than 141 kilometer per hour design wind speed. So if you look at this graph here, this shows month in 2020 from January to June for 4 different locations close to the subject property. So if you look at them, the maximum wind gust was 89 in May, 89 kilometer per hour. So it's really lower than the design code. So then we said, okay, let's get a look closer at the drawing because the wind gust was not above the design. So what was the issue? So if you look at this here, so the top one here shows the as-built drawings, and the bottom one is just a photo of south frame and north frame. So two diagonal braces on the north wall. So this is a north frame, north wall, on the sides of the sliding door, and one brace on the west and end of the south wall were observed. So no diagonal braces were noted in either the east or west walls or across the bottom chord of the roof trusses. So in addition to resist gravitational loads, or we call it downward vertical loads, such as self-weight, own weight, snow loads, these are gravity loads. So a structure must also be properly framed and designed to resist lateral load that would be impacted from wind pressure. So the farm buildings did not have adequate framing to resist lateral load. So only discontinuous bracing was observed on the north wall on either side of the sliding door. So you can see that here. So um, then we came and look at closer at the plan view of the drawings just to understand the framing and the structure of the building. So as you can see here, this is a plan view. The north and south end walls, so this is a south, this is a north wall, were the only members and only part that providing resistance to the wind blowing in the east-west direction. So the 24 feet wide sliding door here, uh, that opening reduced the stiffness of the north wall by approximately 50% compared to the south one. And so this imbalance, so I just zoom in here, this imbalance between the stiffness of the end walls resulted in the development of twisting of the building under wind pressure, acting in the longitudinal direction. So the twisting of the building lifted the post on the north wall east of the sliding door here. So this was the location we had problem. So if you look at here, the imbalance or the difference between center of mass and center of rigidity cause the twisting of the building. The more distance you have between these 2 points, the more twisting building would experience. So just for your information, the center of mass is the point where the entire mass of the floor acts, and the center of rigidity, or sometimes we call it a stiffness, is where the entire stiffness of the building acts. So that obviously clearly answer us that what was the issue. So um, just to summarize why the building lifted, so obviously we couldn't find no evidence that the subject farm building was properly engineered. And also, as shown in the previous slides, the wind pressure never exceeded the building design code design of 141 kilometer per hour. So we found significant pre-existing structural deficiencies render the building particularly vulnerable to twisting and uplift under the wind load. So, but for the pre-existing structural deficiencies, the farm building would not have sustained the reported damage because it lacked adequate lateral load resisting system, and roof trusses were widely spaced. So, also wood posts are typically supported on concrete piers or sonotubes that extended about 4 feet minimum below grade. The posts of the farm building were 6 feet deep in the ground without any bearings, which is analogous to a sticking needless in the ground. So the steel beam may have helped post to resist vertical downward, but only resist to uplift forces was because of the friction between the post and the soil. So although it was well intended, replacing the soil around the post of the farm building with gravel, using hydrovac technique most likely weakened the resistance of the embedded post to uplift because gravel has a lower friction capacity compared to clay or silt. So at the end, uh, looking only at the overall behavior of the structure rather than details would be better. We should not just focus on the details, and having experienced engineer to looking at the overall behavior, such as twisting of the building here, would definitely be one of the items that I would focus more on. With that, I'll pass it on to my friend, and I would be happy to take any question. You can submit your question in the Q&A, and we would be happy to answer that. I'll pass it on to Adam. Thank you very much.
Thank you, Amir. I'll just share my screen here. Just making sure you can see that.
Perfect.
Okay. Yes, so thank you, Amir, and welcome. My case study today is about a group of sand bins that collapsed. So I'll just get right into it. So this was a industrial facility. They were selling frac sand for the oil and gas industry. So frac sand refers to the hydraulic fracturing process. So this sand it's got a particular grain size and quality, just I guess that's used for that process. They were expanding their facility, and they added a group of 4 bins. And this here is sort of a bird's eye view of half the structure. And over here we've got a kind of a side view to show you what this addition looked like. So it's a steel frame to elevate the bins, and that way the trucks can drive underneath, and then this cone hopper, they can receive a load of sand that way, and then drive off. Looking at the top view, so there's that those columns and beams to elevate the bins. Each bin sits on its own ring frame. That's what's in green here, and at the 4 points was a load cell, so that basically they can keep track of the weight of each of the 4 bins, so that for the purposes of keeping track of how much sand goes out and how much sand they put back in when they refill the bins. So these bins each had a nominal capacity of about 160 tons, or that's 320,000 pounds roughly. So pretty substantial amount of sand. So the structure had been recently constructed. They had just recently filled bins 1 and 3. Bin 4 was still empty. And on the day of the incident, bin 2 was in the process of being filled. And then some loud noises were heard coming from the structure. So they stopped filling and kind of sounded the alarm, keep personnel away from the bins. And shortly after that, bins 2 and 3 came crashing down. A little while later, bin 1 also collapsed. And then bin 4 was removed just to make the site a little bit safer for investigation, because it did present a hazard at that point. So at the onset, there was sort of blame being suggested in all directions. Could it have been something to do with the bin? Could have been something to do with the load cells. The designer of that structural steel frame to elevate those bins, the fabricator of the steel components, The erector, in this case, is not the same party as the fabricator. So, you know, the party that put everything together and did all the welding on site. And then also in this case, there was a steel pile foundation. And so is it possible that the steel pile installer, you know, did something wrong? So looking back at that top view, so I've got the bins number here now. So bins 2 and 3, which collapsed first, there are the middle bins. This red-ish girder is supporting all 4 bins on us, and each girder is supported on 5 columns. And we we started by analyzing the entire structure, and we didn't find anything seriously, you know, any indication of a problem with, you know, the columns or the beam sizes. Everything seemed to have been sized correctly. We were able to rule out the foundation and the bin and the load cell pretty quickly. But after ruling out the members themselves, the beams and the columns, we had to take a look at the connections between those parts. So when we started honing in on the connections, we identified this critical connection here at the middle column line. And so what this was originally envisioned as, and when it was designed, was that this would be one continuous girder across 5 columns. But then what happened at some point was that was changed so that it was 2 girders and it was joined over the column. And that turned out to be very important. So looking closer at that column connection, so this is the top view. So we see this is the girder. This is how it was originally envisioned, continuous over that column. And the column has a cap plate. And this is the outline of the column itself. And then looking at it from the side, that's the I-beam, wide flange beam we call it in the engineering world. This is the flanges of that column there. So you're looking at that flange and that flange from the side. And this is the web there, and that's the cap plate. So that column, it was originally intended to be continuous, but it was changed to this. So now the end of this beam is sitting on the plate and nothing else. There's nothing under the beam directly below that plate. So it's just sitting on a little patch of the plate. And this plate the plate itself is not designed for that type of loading. So when we analyzed this condition, we identified that it was significantly under-designed. So this is what happened to the plate. You can see how it's deformed substantially. So we analyzed the plate using a yield line analysis, and we estimated the failure load to cause this type of failure would be about 62,000 pounds. So way less than what it needed to be if that plate was supposed to support the beam the way it was built. But this alone was not. This alone would not have brought the entire structure down. And in fact, what happens once it starts to yield, it starts to behave like a stretched sheet or a clothesline or something. So it actually would still have reserve capacity as long as nothing else goes wrong, which might have given enough time for someone to see it in an inspection and give some warning. But that's not what happened, because there was another problem. So the end of that beam, because it was not continuous, it was split. So now the end of that beam is more vulnerable to a failure called web crippling, and that's what we see here. So this web kind of folded in on itself from the stresses at the end of the beam. So we predicted a failure mode of about 80,000 pounds, which was awfully close to the estimated load at the time, like when the failure occurred. So what happened with the flex, that plate that this was sitting on, as it started to yield, it kind of reduced the effective length that this beam was sitting on, the effective support length, and then this web crippling occurred, and then the final straw was just the bolts kind of holding everything together, snapping and tearing out. So this collapse of the sand bin structure and significant interruption to their business all came down to a single connection that conceptually was changed, but that decision to change that connection was not followed through and checked to make sure that we had a load path that was still acceptable. So the column cap plates first began to yield. That reduced the effective support length for the beams. Beam web crippling occurred, and then finally the bolts holding the beams onto the columns failed, resulting in bins 2 and 3 collapsing. The extensive amount of damage to the structure just in the process of collapsing resulted in bin 1 also collapsing. And with that, I will hand things off to my colleague, Navi.
Thank you, Adam. So let me share my screen. Okay. So do you see my screen?
Yes.
Okay, thank you. Welcome everyone, and thank you, Adam. So I'm going to present the fourth case study, which is the sudden collapse of a church's gable roof. So the building was a single-story church, which was over 100 years old. That would be this part of the building. And there was an extension to south of the building that was added in 1960s, which was this part. The roof was of gable type, and the roof ridge was along north-south direction, which is this direction here. And the whole building was of wood-framed construction. The insurance was that the roof collapsed under heavy wet snow in late winter. Now, why is this a complex claim? First of all, it was unsafe condition. I could not get inside the building or even get around the building to see the connections or the failed members. The other factor is the nature of the incident. By that, I mean the sudden roof collapse of a public building. Now, I should explain that public buildings have stringent design requirements by the code. Usually, we see a roof collapse, let's say in warehouses or farm buildings that have relaxed design requirements. But when it comes to residential buildings, there are strict requirements. When it comes to public buildings, it's even more strict requirements. And the rare failure mechanism, I will explain later that how it collapsed was the edges slid out and the gable roof literally turned into a flat roof here. As you can see, there's no attic left under the collapsed roof of the extension. That's a very rare failure mechanism. Usually if we see some damage to the roof, there's maybe a couple of rafters, they get cracked or they get deflected or the roof is sagging. The damage is usually of this type, but for a roof to collapse, for the entire roof to collapse like this is a rare case. And the claim value was about $1 million. Now, for investigation, we started the investigation and we noticed that, as I mentioned, the collapse was only concentrated in the roof of the extension building. The original building, the roof was almost intact. As I said, it was unsafe. We used drone to closely look at the details around the roof edges. And also we flew the drone inside the attic of the standing roof. And we looked into the design ground snow load based on the code of the time the extension was built. That was NBC 1960. Based on the code, it should have been designed for 33-inch of ground snow load. And then we looked at the historical weather data and found that on the date of loss, the ground snow load was 21-inch. And the maximum historical ground snow load for the location of the building was 53-inch. So right here, you can see that had the building been designed properly to the code of the time, it would have easily carried the snow on the date of loss. So right here, we can say that there must be something wrong with the structure. Now, we should see what was wrong. Before I get into finding the deficiency, I like to talk about a typical structural analysis and details of a gable roof. So here I'm showing the section of a gable roof. So these are the rafters. You have ceiling joists here. These are columns. And these are collar ties. Usually you have it every other rafter. You have gravity loads. These are the weight of snow and the weight of a material. So these are gravity loads coming vertically down. They're carried by the rafters. They produce compressive forces in the rafters. These compressive forces, they produce because of the angle of the rafters with the horizontal, they produce a horizontal force here and a vertical force here. So the vertical force is taken by the column, so you will have compression in the columns. The horizontal force is taken by the ceiling joists. So you have tension in the ceiling joist, which means the rafters must be properly connected to the ceiling joist. Otherwise, this edge will just slide out and the roof just caves in. Here's the detail of a typical construction at the edge of the roof. You have the rafter, you have the ceiling joist, you have the rafter, and the ceiling joist should be face nailed to the rafter. And here you have the soffit and fascia board. Now let's look at this particular building, see how it was built. You had the rafter. It was sitting on a plate. The plate was fastened to a rim board, and here are the ceiling joists. So in the photo, you can see the ceiling joist here. This is the rim board. The rim board was up against the ceiling joist. These are the rafters. They were sitting on a top plate, and this is a piece of the OSB. So this is a piece of OSB. This was a top plate, and the rafter was sitting on it, and the rim board was just connected to the ceiling joist. Now, the problem here is, as I said, there's tension in the ceiling joist, which means these nails were in tension. And the nails, as you know, they have a smooth shank, and they were embedded in the end of the ceiling joist. So they are very weak in carrying tension, so they could easily withdraw from the end of the ceiling joist, which is what's happened here. Again, the detail of this particular building and a typical detail. In a typical detail, we have, let's say, 6 or 8 nails face nailed to the rafters, face nailed from the ceiling joist to the rafters. In this configuration, the shank of the nails are not in tension, they are in shear. But here, when you nail it like this, the nails are in tension, so they just pull out. Now, this is not a sudden failure mechanism. This is gradual, which means over many years, over many winters, they pulled out gradually, and then eventually on the date of loss, under some snow, it just collapsed. And now this is an image we took from Google Maps that was taken a couple of years before the date of loss. And you can see a significant sagging of the roof. So see, this is the original building, like the roof is good. Here you can see it's just sagging down, exactly like a saddle. So why the church roof collapsed? The probable cause was pre-existing construction deficiency. It was not the snow. And the construction deficiency was the improper connection of rafters to the ceiling joists. And the collapse was a result of gradual failure of connections over many years. It was not a single incident. And depth of roof snow on the date of loss was less than the designed snow load. In other words, if it was designed properly, it would not have collapsed. The lesson learned from this example is presence of snow on top of the roof does not necessarily mean the snow caused the roof to collapse. So based on the case studies that we presented in this presentation, what to look for in a complex claim. First of all, building safety and security is paramount in all claims, especially complex claims or large claims. A structural engineer should be attained from the get-go, assess the site, and give instructions on the safety measures. And there are obligations under orders to remedy unsafe buildings. When there is severe damage, the city usually issues an order to remedy an unsafe condition. Under that order, there's an obligation to retain structural engineer to assess the site and give safety instructions. So by retaining a structural engineer from the get-go, you're saving time and you are satisfying these obligations from the beginning. The impact or role of pre-existing conditions are very common in different losses, also in large losses. As you saw in the previous scenarios presented here, pre-existing conditions can be deterioration of a masonry wall, as in the case study by Yasser, or lack of bracing, as in the case study by Amir, and just lack of a couple of stiffeners or discontinuity of the beam in the case presented by Adam, and also a poor detailing in this church. Mandatory code upgrades must be conducted as needed. When there is severe damage and it needs severe repair, major repairs or reconstruction, then it has to be upgraded to the current code. Otherwise, it will be unsafe. Additional building permit requirements are needed if the footprint of the building is going to be changed, and also if it's a heritage building, that's an additional permit that needs to be obtained. If it's beside a lake, you need to get a permit from Conservation Authority. If it's beside a highway, you should get permit from Ministry of Transportation, Ontario. And small changes that may lead to complex approvals. Again, if you are changing the footprint, it needs approval. If the services are going to be replaced, like HVAC system, it needs approval. The septic system needs approval. So these things need to be considered in a large loss. Thank you very much, and we are happy to take any questions.
Awesome, thank you so much. So you can stay on this slide, Navi, and we will just ask questions for the next 2 minutes so that we can have a short break and then start again in the next the second hour. So the first question here for case study number 3, the bin collapse. Was there an issue regarding the welds or fabrication process? So I believe that was Adam.
Yeah, so I mean, there was some evidence that some of the welds were substandard quality, but it wasn't like it wasn't throughout the entire structure. Like we didn't see poor welding universally. We just saw a few welds that lacked good fusion, but most of the welds that we saw exhibited what we call a shear lip, which indicates that the weld failed by overloading, but that the weld did its job essentially. So it was almost like a red herring. Like there was some evidence that not all the welds were up to snuff, but it wasn't at all related to the collapse.
Okay, I see here just a quick question. What was the quantum of that bin collapse loss? Like, ballpark it for us.
Yeah, I don't recall. But I think it was on the order of $2 million, like all told.
Okay.
Yeah.
Okay, cool. Next question. For the sand bins, was it simply that the bins were not designed with sufficient load-bearing safety margins? Well, you had kind of covered that in the placement, right? The placement.
Well, it was that changing the conceptual, that the concept of having one continuous girder, changing that to 2 girders and splitting it over the column, and the way that was executed, like they didn't really. That change was not properly reviewed, and the connections at that joint was not reviewed. So there wasn't any safety margin because of that change.
Okay, and was it determined who made that call? Who made that change? Was it the engineer, contractor, builder, owner?
In this case, so in this case, the designer and the fabricator were the same company. So it was them.
Yes. And last question, you say that the presence of snow on a roof does not always translate to the cause of loss, but can you say that the same loss would have occurred on that day without the presence of snow? So that would be a Navi question.
So, sorry, would it have happened without the presence of snow?
Correct, yes.
It's very hard to imagine for it to happen without the presence of snow, because without the presence, the load on the roof is very minimal. But I mean, it would have eventually happen under some snow later on, or no?
Yeah. Would it be accurate to say that the snow essentially aggravated the deficiency, and as a result, like if
so the snow was something that made the deficiency come to surface, like
yes,
it's like Yeah,
We call it a trigger, George. The
Okay.
snow was the trigger who exposed the deficiency and the pre-existing condition. Any structural member that would not see load would not be put to the test to see whether it
Yes.
would withstand the design load or not.
But I guess if that deficiency in construction was not present, it was designed correctly, the amount of snow that laid on that roof would not have caused any sort of damage. Would
that is
be
correct.
accurate?
That is correct. Yeah.
Cool. Okay, great. So thank you so much to all of our presenters and all the folks that are submitting questions. Thank you. Make sure you get your questions in early because those are the ones that we're having time to cover. We're going to take a 3-minute break and we're going to start on the second hour on the same topic on structural losses. So this is the second part of the complex structural claims presentation. And we're fortunate to have two presenters from Torkin and Mains, looking at this topic from the legal side of things. So first we have Chris Valente, who's joined us. He's a partner of the firm in the Insurance Defense Department. He has a broad insurance litigation. It's a large insurance litigation practice, including fraud actions, environmental impairment, remediation, architectural flaws, product liability, personal injury and coverage opinions, subrogation claims, and mortgage default proceedings. And he attended all levels of Ontario courts. Today, we also have Kayla Quinter joining us. She actually joined us as well last year in our national tour. So great to have you back. She's also a partner of the firm in construction law and litigation groups. Her practice includes broad construction litigation, acting on behalf of general contractors, subcontractors, sureties, suppliers, and public and private owners, including municipalities, on a variety of construction-related litigation matters. Kayla regularly appears before judges of the Superior Court of Justice and construction lien associate judges. So we'll hop right into it.
Yes, thank you, George. I want to start off by saying that this is a real pleasure. We appreciate this opportunity. Origin and Cause has been instrumental in helping us to refine and prepare this presentation. Mark St. Marie and George specifically. And I'm just very excited to actually be in a situation where I'm able to do something a little bit different from the normal wear and tear of this pandemic. This presentation is a welcome change. We wanted to start off this presentation by presenting a number of different insurance policies that might respond to the presentations previous to mine. We looked at professional liability policies, builder's risk, CGL, wrap-up homeowners. And we realized that this was a bit of a fool's errand, that in a 30 to 40 minute presentation, we might only scratch the surface. So George suggested we present a few case studies, practical examples from our litigation practices and coverage practices. And I will say also that Kayla used to be in the insurance department, and she's quite a capable coverage lawyer as well. We narrowed it down to 3 case studies. I'm going to take you through them now and hopefully get through all of them. The first one is a case study on a cracking foundation. The facts of the case were that a foundation damage was found in a heritage building. There was an adjacent high-rise construction. Damage was noticed during the excavation and shoring of that high-rise construction. And so the high-rise contractor was put on notice. And here you can see This is the east wall of the heritage building that was damaged, and a pretty good look at the excavation and shoring work that was being performed by the contractors to the east. I was going to point out that I wanted to point out that the shoring work is all fairly flat and uniform across the surface. It's consistent. And I want you to keep that in mind because I'm going to refer to it again in an upcoming slide. This next slide shows the east excavation and some wood lagging that was installed. Not exactly sure why it was installed, but there was interior damage to the foundation of the heritage building on the other side of that lagging, and potentially a source of the foundation damage to the building. So the damage itself included a 3x8 section of the east foundation wall. It was bulging into the occupied space. Cracking was later found in the east exterior wall at the roof interface, vertically in line with the section of the damaged foundation. And the excavation on the east side of the building was assumed to be the cause. Looking at the causation issues, the damage was likely caused during the excavation and scraping of the east wall by the excavator bucket. That's how that uniform surface I referred to was achieved. However, an engineering inspection determined that the cracking and bulging was pre-existing. So we had a problem. The complexity in this case was, what damage was pre-existing versus the damage caused by the construction. The insurance in place, 3 policies. There's a builder's risk policy. It would refuse coverage as they typically apply to only property under construction and the project itself where the high rise is being built. Okay, so what do we have left? We have a CGL and a wrap-up liability policy. Those insurers refused to become involved because the damage was not caused by any apparent negligence. The expert opinion determined that the damage was pre-existing and naturally occurring over time, given the age of the building. But on the other hand, there's an obvious construction disturbance to the east, along with the complaints by the occupants. So we've got a real pickle. The matter looked to be headed toward long drawn out litigation, and yet the matter resolved within only a few months. And why? What unlocked the stalemate? Reason one, the ongoing monitoring by the engineer revealed further and additional cracking in the building. The additional cracking was occurring at a rate greater to natural deterioration. The accelerated rate of the cracking could only reasonably be related to the construction vibrations. So the ongoing damage to the heritage building exposed the liability insurers. But there's still this question as to whether the contractors were negligent. Just because this cracking is taking place, it doesn't necessarily mean that the contractors breach the standard of care. The second reason, the heritage building owner secured a tieback and crane swing agreement with the general contractor before construction commenced. The tieback agreement contained an indemnity clause favorable to the heritage building owner. The tieback agreement also included a clause ensuring that the general contractor secure insurance coverage for liability assumed in contract. The tieback agreement exposed the liability insurers as a result. The agreement itself, the policies both had insured contract exceptions to the typical exclusion for liability assumed in contract. And I know that there is some debate over what those should apply to and when. And in some cases, the insured contracts that provide an exception to the liability and contract exclusion are quite limited. They're sometimes listed as very specific types of contracts. And if you don't fall into any one of those categories, then you don't fall into the exception. And in other cases, it's generally contracts that are usual to the business of the insured. In this case, this type of contract, this tieback agreement, was usual to this insured's business, and so there was exposure. When we look at the indemnity language, it is significantly broad. I've highlighted the portions of this indemnity language and sort of faded the parts that are less important. So I'll read it out. The company agrees to indemnify and save the owner harmless from and against any and all claims incurred by the owner and arising directly or indirectly out of or in relation to the exercise by the company of the rights granted to the company under the agreement. So right there you have the words directly, indirectly, or in relation. And the case law generally, looking at this type of wording, will choose the broadest wording and apply it. And so whether you think, indirectly is broader than in relation to or vice versa, that determination will be made by a court, and they will apply the broadest language, which I understand, I believe, I'm referring to a memo sort of off script here that I've read a few years ago. I believe it's in relation is the broadest language. And if that's not enough, it goes on to say, and or in connection with the construction and completion of the project. So whoever drafted this indemnity agreement tried to touch on all the different ways that there could be some kind of connection to a liability. And then further, if that's not enough, it says that the company agrees to indemnify the owner in respect of all claims arising out of any damage caused to the lands and or any buildings, the heritage building itself, arising directly or indirectly from or incidental to, again, all the different types of language you might see used once or twice, but it's all the players are here. With respect to the company's rights granted under the agreement, again, quite broad. And then it goes on to refer to any negligence or omissions by the company. And then the final paragraph basically brings the GCs, the subcontractors, into the fold, making the general contractor responsible for all of them as well. So again, whoever drafted this, the intention was clear. It was to put any and all type of exposure possible onto the insurers. And in this case, given that the exclusion for liability assumed in contract were either removed or those liabilities fell within the insured contracts exception, the goal seems to be achieved. The takeaways: ongoing construction projects may include ongoing monitoring capable of altering initial engineering opinion, where there are additional planned inspections and or vibration monitoring. Those, if that type of work is going to continue, then I think it's important to stay on top of those developments. It's not a situation where you can just close a file because of an initial engineering opinion that cracking is pre-existing or the result of natural wear and tear. It certainly wasn't the case in this example. And it is important, I think, to retain an engineer to vet the inspections and monitoring performed by the adjacent landowner's engineer. We can't just be going willy-nilly based off of what the neighboring property's engineer is concluding. Again, another example. This is an example of why that type of additional advice is important to retain at the outset and throughout the continued construction. The last takeaway is that the tieback agreements need to be identified early, given the potential and significant unanticipated exposure, and if possible, before it is executed by the insured, and in order to appreciate the insurance risks before the work begins. Now, that's going to be more difficult to do in the CGL context. You may not know what an insured is doing under the assumptions that it's covered under its CGL from day to day, but the wrap-up policies are generally issued on a project-by-project basis, and I think these types of questions are not only relevant, they're essential to knowing what the risks are and understanding what a tieback agreement might say and whether an insured intends to enter into one. Okay, we can move on to the next case study. I'm moving quite quickly here in the interest of time. I want to make sure we get to the end. This one is a roof collapse. And I'm happy that Nabi provided his Gable Roof analysis just only a few moments ago, because some of it is going to be helpful to conceptualizing what's taking place in this example. So what we have is a residential home with a large sprawling roof. The roof shifted under load of snow, causing significant structural damage throughout the home. The homeowner's insurer denied coverage and based that denial on the exclusion for faulty workmanship. Now, the reason I chose this particular example is because I think it's a practical, down-to-earth example of damage to a home, which everyone can sort of wrap their heads around. And because the exclusion relied upon was the faulty workmanship exclusion, and it has broad application across a number of different types of policies. And so the issues can overlap somewhat depending on what you're working on. So here is a photograph of the home itself. As you can see, it's quite a large frontage. The roof is quite wide. This is a bungalow. So what it lacks in square footage, floor by floor, it makes up in its footprint. You'll see in the next slide, this is an aerial view of the home. And the top of the picture from Google Maps here is showing the front of the house. The street is just out of view. And then in the back of the home, we see this red right angle, and that is showing the area of the damage. Underneath that right angle was the den for the home, and it had a cathedral ceiling. Here is an exemplar photo of a cathedral ceiling to give everyone an indication of what the problems were. So you can see in this picture on the edges of the 2 walls, there are 2x8s or 2x6 ceiling joists running across the entire length of the room. Now, if those ceiling joists were spaced out across the ceiling of the room, you would have a flat ceiling. But in order to create that vaulted or cathedral appearance, you have to remove the ceiling joists. And that requires these rafters that you see in this particular example to be adequately braced in the absence of those joists. The next photo is a picture of the framing of the actual home itself from 30 or 40 years ago. And we are fortunate enough to get this photograph. And what it shows to the left is a wall separating the den and the kitchen. And this red line here is just something that I've added in. It's an underlining of the edge of the kitchen wall. And just to the top of it, it's very difficult to see given the lighting, but you can see there are a number of 2x6 ceiling joists that are cut. And what this blue line represents is what we believed was the intention of the designer to extend those joists from this kitchen wall across the den and out to the exterior wall that ended up protruding and bowing outward under the snow load when the cathedral roof failure occurred. Had that blue line representing those joists been installed, it would have provided additional support for that exterior wall, pulling it and securing it against this internal wall for the kitchen. Okay, so we have a problem now. And are we dealing with faulty design, or are we dealing with faulty workmanship? This was an old construction from the 1990s. The design records were not available at the township. The town had switched corporate identities over the years, and documents were lost. So there was no way to tell if the issue was related to design or workmanship. So why is that a problem? Well, the burden of proof is the issue. The plaintiff has the burden to prove a claim falls within coverage. I think we can all agree on that. And then the defendant insurer has the burden to prove the exclusion it relies upon. But in this case, insurer could not prove the faulty workmanship exclusion because it was equally possible that the design was flawed. This case of Dawson Creek versus Zurich is a case where the British Columbia Court of Appeal looked at very, very similar facts. Oh, and I should mention that leave to appeal to the Supreme Court was denied. Virtually identical facts, as I said. It was an arena, roof collapsed under snow load, building was 40 years old. There's no records of the original design. And you have this issue of, are we dealing with faulty workmanship or faulty design? The argument was essentially that it must be one of them, right? If the builder failed to install the joist, then it's a workmanship issue. If the joists were never supposed to be there by design, then it's a design issue. One of the exclusions must apply. But the court didn't accept that reasoning. The insurer still had the onus to prove one of the exclusions. Evidence had to be established that would fit into one of the exclusions and satisfy the wording of it. But the lack of records and the lack of facts made it impossible to prove any of the exclusions applied. And so the insurer in Dawson's Creek couldn't prove either exclusion. The court further cut the legs out from under the inherent vice and latent defect exclusion, questioning, what does it actually mean? What should it apply to? And especially without any evidence to prove a design flaw, very difficult to interpret those words. There's a similar case from Ontario. This is the famous Canadian National Railway case, Royal and Sun Alliance, 2008. This is the state-of-the-art boring machine case. And in that case, the court said that inherent vice is difficult to define. Some courts have referred to it as deterioration of construction materials. So you would need to have evidence of deterioration. That wasn't going to be likely on our particular set of facts because we're dealing with, a failed roof. Deterioration was not really something that we were going to establish. And then Dawson's Creek, the Court of Appeal reasoned that you'd have to also prove that the defect was in fact latent. In other words, that as part of this, a latent defect exclusion, you'd have to show that the defect was not discoverable upon inspection. That was also going to be an issue. And they also went on to say that it's a exclusion that should be considered as distinguishable from construction defects, which are specifically excluded under the workmanship exclusion. And further, they went on to say that the inherent vice and latent defect exclusion is something that generally should apply more to perishable goods. So we knew we had only one option, and that was to prove the faulty workmanship exclusion and to forget about this idea that latent defect or inherent vice was even going to be an option going forward. So how did that happen? Well, we were able to acquire a copy of this blueprint. And what it shows is this yellow line here. And you can't see the words, but the words are there, I assure you. It says joists, plural. And it's an intention to connect this exterior wall to the exterior wall that failed under the cathedral ceiling to provide additional support across the back end of the home. And how did we acquire this? Someone came up with the brilliant idea of getting a copy of the subdivision plan and identifying homes with similar, where similar models had been built. Those homes were visited, and this turned up. And without it, it would have been impossible to prove the workmanship issue, because it clearly shows that the joist was supposed to be there and that the builder had gone rogue. So we weren't through the woods yet. We're talking about an all risks homeowners policy, including specific collapse coverage. And the exclusion wording being relied upon is set out there in the slide. We do not insure the cost of making good faulty material or workmanship. And then there's the exception, the common exception that you often see with this exclusion, which is unless physical damage not otherwise excluded by this policy results, in which event this policy shall insure such resulting damage. So this is the resultant damage exception. And I'm sure most people are familiar with lead core, the leading case on the topic. The window washers wash a number of windows in a commercial building. The windows are all damaged. And the court ultimately determined that the exclusion only applied to the cost of the window washing itself, and the resultant damage to the windows was covered. In lead core, this exception was written into the policy. In Monk, it was not. And Monk is a case where you're dealing with a homeowner's policy as opposed to the commercial policies in the lead core decision. And so Monk was more relevant to our situation. And without this exception, was the court going to consider resultant damage as an exception for the plaintiff? And in Monk, the court ultimately decided that the exception could be read narrowly and focused on only applying to this underlined portion here, the cost of making good. In other words, they said that we do not need to consider whether an exception exists in the policy for resultant damage or not. If the exclusion will apply only to the cost of making good the workmanship, then it flows that the resultant damage would always be covered regardless of whether the exception is present. Now, the court claimed that it wasn't reading in an exception here. It likely was, but the reasoning is difficult to argue with either way. And so what the plaintiff took from this was an opportunity to say, my roof collapsed because lateral bracing between the rafters in the cathedral ceiling wasn't present. And that's shown here in this exemplar photo. You can see these dark wood rafters. Again, there's no ceiling joists. And the plaintiff's argument was a relatively inexpensive fix with respect to lateral bracing would have prevented the whole thing from coming down. Okay. So more specifically, the insured's position was that the engineering opinion was that there was a lack of lateral bracing, allowing the rafters to shift in the same direction under a load of snow, almost like dominoes. The same forces push the exterior walls outward, and the lack of lateral bracing could be remedied with inexpensive steel strapping, the cost of making good. The outcome of this argument, or the point to this argument, was that everything else was resultant damage. The roof, the main floor structure and finishings, the basement foundation and finishings. Okay, fine. So we still needed to look further into the scope of the damages, and this is what was discovered. What you have here is a drawing that's sort of giving you an idea as to how the house was designed and actually constructed. What you have is a roof within a roof. This white line depicts the cathedral ceiling. This orange line is meant to show the joists that were supposed to be in place but were not. Okay, fine. But upon further inspection into the damages into the roof itself, because the entire roof was damaged by this collapse and required extensive repair. What was noticed was that this blue line right here, which is a collar tie, which Navi spoke of earlier, it was overspanned. It was twice the length required by the building code. And these rafters, which were supposed to be spaced out every few feet, were actually spaced out twice the length of the building code requirement. And what we ended up determining was that you had a complete failure to by the builder to install the roof to code or to the design. The rafters all had to be replaced. Collar ties all had to be replaced. The joists had to be installed, and the cathedral ceiling had to be braced properly. And so ultimately the resolution in this case, hinged on this question: what was the scope of the resultant damage coverage exception? The builder failed to construct the roof to code, and ultimately the entire roof was excluded for faulty workmanship. The main floor and basement were likely resultant damage. And I think it's important as a takeaway for this particular example to consider the fact that the scope of the resultant damage may include larger structures when facts point to a number of overall workmanship failures. And typically, this exclusion applies to only very limited items, so often that are of an insignificant cost, such as this lateral bracing that was being argued in this case, or the window washing in the lead core case. But it does appear possible that where there are larger structural issues and that the contractor is responsible for a multitude of them, that it is possible to exclude a larger piece of the loss. And I think that this can potentially apply similarly across several policies, both commercial and residential. Okay, the final case study is a concurrent coverage case. The facts of this case are a flood. It occurred at night during off hours. There's damage to a water line causing a leak. And the water damage occurred while an addition to a commercial building was under construction. And there was a builder's risk insurance policy in place during the course of construction for the addition. And there was first-party property insurance also in place for the existing building. The water line failure caused damage throughout the commercial building, both the existing building and the addition in the course of construction. So I'm sure some of you can see where this is going. The concurrent coverage was the first party property for the existing building and the builder's risk COC. The next photo shows you a picture of the water line that failed. Very difficult to ascertain cause. You can see that the coupling engages a fair portion of the pipe that it's attached to, leaving only a limited space for the other pipe to adhere. Potentially this is an installation issue, but then on the other hand, you have these odd cuts in the pipe. Is that an installation problem with just a lack of care? Was it intentionally cut? Did the coupling slip? Was the pipe pulled during construction, causing issues with the coupling? Very difficult to tell. The issues that came up, well, who is covered under the builder's risk? Well, that would have been the owner, also covered under the first party property policy, GC subcontractor, security staff, and it also covered the suppliers, which is not always the case, but it was in this particular instance. This all influenced the investigation. The failed water line was removed and stored for destructive testing, and the representation at the testing was, intended to include the anticipated insureds we saw on the previous screen. Those interviews were conducted by the insurer's investigator and included all representatives of the anticipated insureds. And the resolution on this issue was, on this loss, was, well, all those connected to the water line were seemingly covered under the builder's risk. Therefore, further investigation was determined unnecessary. Destructive testing was never carried out. Cause was never determined. However, a chain of custody and preservation of evidence issue arose nonetheless. So the cautionary note here is, what about the manufacturer? Was there a manufacturing warranty that would have responded to this loss? If so, was there a breach of that warranty by removing the pipe and not ensuring a chain of custody, not providing the manufacturer with an opportunity to inspect in the circumstances? Were they a potential defendant? Or was this not a manufacturing issue at all, in which case this was all a red herring? And even if there were some exposure on the manufacturer, there's a potential for a limited liability clause in the warranty wording as well. So whether this manufacturer would have ever been responsible is difficult to say and potentially unlikely, but we've included it as a cautionary note because it's a party to not forget about in these situations, and to include in the investigation in order to honor any warranty that could potentially be available. Moving on, who is going to cover this loss? The builder's risk insurance applied to the property in the quote course of construction. The first party property insurance applied to the property, generally speaking. The issues that arose were subrogation. The first party property insurer was claiming to be prejudiced by the investigation of the builder's risk insurer because that investigation was mainly carried out by the builder's risk insurer, but that was a sort of secondary issue. The main one was jurisdiction. The entire building versus the addition under construction. How are the two insurance companies going to divide this loss? And the problem was that the debate over the jurisdiction caused delays and potentially caused a prejudice to the insured because of those delays prevented the repair of the building from occurring in a timely manner. So what you have is a delay that caused the builder's risk soft cost coverage to inflate, while at the same time caused the first party property insurer's business interruption coverage to inflate. And I'm going to propose a resolution for this type of situation at the end of this case study, but just keep those cost increase issues in mind. Looking at the case law, Pre-Eng v. Intact Insurance is a 2019 decision, very straightforward. A construction project involved the repairs to the roof over a school gymnasium. Only the roof was in the course of construction. Gymnasium floor was damaged, however, during the course of construction. Okay, what did the policy for the builder's risk insurance say? It said that insured property, this form insures the following items at the project site, which included the building and the lands, the whole building, but was limited to only property in the course of construction, installation, renovation, reconstruction, or repair. So how did the court interpret this? Was this insurance to apply to the whole project site or just property in the course of construction, the more limited coverage A there? The court concluded that I find the words property in the course of construction, installation, renovation, reconstruction, or repair are sufficiently clear to exclude the gym floor from coverage under the builder's risk policy. The gym floor was not being installed or renovated or reconstructed, and there is no evidence to suggest that it was. So on our facts, this raised some difficult questions. Clearly there's a distinction being made here that only property in the course of construction is covered under the builder's risk. And certainly the water damage is indiscriminate. It doesn't just decide to, damage the addition versus the existing building. It damages everything. But the existing building, it wasn't in the course of construction, but yet it sustained water damage. And the builder's risk covered the addition only, and it clearly was in the course of construction. So that seems clear enough. But when you also consider the fact that the water line itself leaked in a portion of the existing building, it complicates matters even further. And I think if you were to try to resolve that particular issue, because this case study doesn't have a particular resolution, but I'm proposing that if you were to try to resolve that, the fact is that you have this liability for the water pipe breaking and it failing during the construction of an addition by the contractor's hand, essentially. But that is only a liability related to the actual pipe itself. The damages are quite separate. The damages flowing from that are throughout the existing portion of the building, which I think, in fairness, would put the first party property insurer on the hook for the repairs. And of course, then the proposal then would be for the first party property insurer to pursue the installer for in a subrogated claim. That seems to me to be the way that you might want to deal with that type of scenario where there is a liability occurring in the existing building during what is otherwise a course of construction for an adjacent portion of the building. So I'll end off with some food for thought. Coverage available under both policies, I think in this case, yes. What do you want to do about division of responsibility? Portions in dispute, can they be referred to arbitration? Perhaps that is a way to deal with larger losses. This was a large loss in this case, hard to believe given that pipe was so small, but it was. And perhaps the arrangement to be made is that, the two insurers decide we'll split the damages and refer the true apportionment to arbitration, or one of the insurers potentially steps up and covers the losses on a without prejudice basis to arbitrate. This particular type of solution, however, is only going to really apply to larger losses and not to the everyday sort of cases that have less significant damages and need to be repaired in a more timely manner, which is why I tried to provide some analysis for how you might want to look at a case where there's a damage in an existing building as a part of a new construction. And then finally, the reduced exposure for lost revenues and increased expenses is obviously a desirable outcome and a reason to try to assign some ownership early on in the process. And I think that's it for the 3 case studies. And I thank everyone for following along. I'm going to turn it over now to my partner, Kayla Quinter, to talk about document management in similar types of cases.
Thanks.
Sorry.
Thanks, Chris. That was so thorough and informative. Thanks a lot for that.
I just took over the screen by accident. If you don't mind taking it back, Chris.
Okay.
Sorry to disrupt, guys.
No
Problem. That's okay. Does that work?
Yes, there you go.
Okay, good.
Chris, do you mind going to the next slide?
Yes.
Thanks. So I'll be brief and a lot less technical than the content that we've been listening to so far today. I want to talk about the documents in a complex structural loss, because the documents in a complex structural loss are very different than the documents in other kinds of claims that you may deal with in the insurance context, primarily things like personal injury claims. There are so many documents in construction matters, and one case that Yasser and I worked on together that I think really illustrates the importance of thorough and early document production was pharmacy collapse that we worked on. And in that case, almost everything that could have gone wrong did. Not to anyone's fault, but what happened was that it was a big, complicated case. There were two different causes of the loss, and the insurers needed to sort out which cause they were responsible for, and then subrogate for the portion of the loss that they were entitled to subrogate for. So in that case, there were a number of different adjusters that the file changed hands through, because the file went on for so many years. The first adjuster that was involved retired partway through his involvement in the file. The file moved to a new adjuster. Very unfortunately, the insured actually passed away during the course of the file. And so she was no longer available, of course, to help with any holes in the documentary production. So in that case, it became very challenging ultimately for the insurer to prove its claim on the subrogated loss, because it couldn't prove the business interruption loss, because it simply didn't have all of the documents that it needed. So the lessons that I think we can learn from that are: collect documents early and be thorough, because there's no better opportunity to collect the documents than right at the beginning of a claim. As things move on, they're likely to get, documents are likely to get lost, they may become destroyed, you just don't know. But the easiest time to access and collect the documents is early on. So Chris, if you're there, if you don't mind flipping to the next slide. I just want to mention a couple of the documents, and this is not by any means exhaustive, but some of the main documents to keep in mind. If the construction is ongoing and you're dealing with a claim where contractors, owners, consultants, subcontractors, suppliers are all going to be involved, and you've got to figure out who's at fault, and you've got to figure out potentially overlapping policies. Chris already talked in detail about making sure that you get copies of the policies and making sure that you review the policies in detail. You're also going to want copies of contracts, subcontracts, payment certificates and invoices, drawings and specifications, and that includes as-built drawings, which can be very helpful later on in terms of determining whether the construction was actually built to the specs. And when we talk about contracts, Chris mentioned earlier, crane swing and tieback agreements, again, those can be vital in terms of apportioning liability and determining whether there are any indemnities that are relevant. So you're going to want to make sure that you get copies of contracts between all of the different parties that may be involved. And that certainly goes back to Chris's point about identifying all of the parties early on and understanding who may be liable and who we're concerned with, and then covering off all of the different agreements that may exist between all of those parties. Payment certificates and invoices are not always relevant in these kinds of claims, but as I say, it's easier to get them at the beginning than at the end. So I would encourage you to collect all of the documents relating to payment for the project, because they may be relevant, and it's better to have them and not need them than need them and not have them. And Chris, if you can just go to the next slide. And the last thing that I want to mention is if you're dealing with a project where the construction is not ongoing, so like the pharmacy collapse case that I mentioned earlier, that was a case where there was an existing pharmacy, and the pharmacy was being used as a pharmacy, and it then suffered two different losses in short succession. So we weren't dealing with a construction project issue, we were just dealing with a first party loss. And in that case, you still want to be very thorough. You do want to make sure that you gather all of the documentation related to the loss, and that includes any losses related to the business interruption claim. But as Chris mentioned earlier, it can also be very helpful to try to collect documents related to the original construction. So that might include original drawings, building permits, whatever you can find that may help in establishing liability. So with that, those are all the comments that I wanted to make, and I think Chris and I are ready to take questions.
Thank you. Just took over the screen at the right time. Great. So got a few questions that have come in. We'll take questions for 3 minutes and take a 5-minute break. So first question is, with all the new homes being built, have you heard of existing nearby homes being affected by construction or the cracking of foundation walls?
I can speak to that, Chris, and if you have anything to add, please feel free to jump in.
Okay.
But, that's something that we deal with a lot. I mean, certainly there is always the potential that construction can affect the neighboring properties, and that's especially true if you're dealing with a semi-detached house or row or townhomes. So it's a good question. If your question is, simply, is that possible? Is that something to consider? The answer is yes, absolutely, it's possible. If your question is, what do we do about it? I mean, again, Chris mentioned earlier, tieback agreements. So agreements between neighbors regarding what precautions you have to take to preserve the neighboring property in the course of construction on your own property. It is really important. Neighbors are always tricky in construction projects, and I certainly always encourage people to work with their neighbors and cooperate with their neighbors, because the last thing that you want to do is be in a dispute with your neighbors. But it's important to have the right agreements in place, and it's important to make sure that you're working with a contractor who knows what they're doing and who can take the appropriate precautions. And of course, there are times where you certainly need to get an architect or an engineer involved to make sure that you're taking those precautions.
Yeah, I'd only add to that, Kayla, and I think it's an excellent question, and I think it's especially important because the home prices in Toronto and throughout Ontario are exploding. I have been called in to look at this very situation occurring with homes in excess of $3, $4, even $5 million. As these prices increase, the risks increase. And the short answer here is yes, I've worked on tieback agreements for both homeowners and construction companies on either side of construction taking place adjacent to homeowner properties, and I think it's a relevant question. And as Kayla pointed out, even more so when you're dealing with townhomes, because now you're talking about a number of properties that all share a foundation and multiply the exposure.
I dealt with a case a number of years ago where the owner of one semi-detached house put an addition on the back of their home, but didn't actually dig a foundation for the addition. They just built it, and then when the neighbor went to build a similar addition a few years later, they discovered that the neighboring addition was bearing down on their structure, and they needed to do a whole bunch of structural work to shore up their neighbor's addition before they could do their own addition. And of course, that turned into litigation.
Yeah.
Awesome. Okay. We have time for maybe one quick question. In your case study number 1, can you comment on the degree of liability imposed on the insurer for the damage, considering that the original engineering report suggested that the identified damage was pre-existing, resulted from the age of the building, and had accumulated over time? The ongoing monitoring only identified additional and/or accelerated damage. This suggests only a degree of responsibility imposed on the contractor. Your comments?
Yeah, that's an excellent point. highlights the absolute necessity to have a pre-engineering inspection. You need something to compare the rate of deterioration against. And in this case, it was difficult to do so because the degree of inspection wasn't close enough to identify what was new versus old. And so it became a major challenge to know what damage was pre-existing versus what was new. And it all sort of ended up becoming part of the wash as a result. And, I had mentioned the need to look into whether tieback agreements are being entered into by insureds at the outset of projects, but also ensuring that there's some kind of pre-inspection to compare damage throughout the project is just as vital. And unfortunately, we weren't able to do it in this particular case study.
Cool. Great. Well, thank you so much. Really appreciate all of your efforts, Chris and Kayla. Folks, we'd like to take a 2-minute break, and then 2-minute break, and then we're going to jump into our last topic, complex structure fire claims. This is a very exciting one. So we will start at the beginning of the hour.